Hi, everyone. My name is Jeremy. I work on the communications team at the Molecular Foundry, and I'm here today for a conversation with Sinead Griffin, who is one of the scientists in our theory facility. We're going to talk about quantum information sciences and dark matter and a whole bunch of stuff that I'm really excited about. So, Sinead, can I have you introduce yourself?
Hi, Jeremy. Great to be here. So, I'm Sinead. I'm a staff scientist in the Molecular Foundry in the Theory Facility and in the Material Sciences Division. And my group looks at using theory and calculations to understand quantum materials.
Amazing. So, can you tell me a little more about what the theory facility does? Like, what is your role kind of in the experimental workflow of the Foundry, and how does it differ from maybe some of the other facilities?
Sure. So, in theory, really, our main goal is to understand why a material or why a system is behaving the way it is, and can we make predictions to either enhance that behavior or to make entirely new predictions about new phenomena and new systems that haven't been observed yet.
Wow. Okay.
So, that involves a few different processes, both explaining existing experimental measurements or suggesting new experiments or new materials that experimentalists can
Oh,
explore.
cool. So you get to kind of both be the receiver of an experimenter or researcher who has a result that they don't understand. You can help explain it, or you can kind of be the initiator where you figure out something, you predict something, and you can pass it off to a researcher to go kind of try it in action.
Right, exactly.
That's
So
fascinating.
yeah, so it's a multi-directional. It's like a chicken and egg problem, right? Where does theory fit
Or
in?
a cycle, and at its best, I guess. That's really cool. So can you tell me? I know one of the things that you work on a lot is quantum information sciences. Can you give me like a really quick rundown on what that is, like what quantum computing is, and why it might be useful?
Sure. So a lot of our existing computing framework relies on the fact that systems are what's called deterministic. So it's either in a zero or a one, like the binary logic in our computers.
Got it.
But with quantum computing, we actually take advantage of the fact that when we go down to very small scales, down to the quantum regime, these zeros and ones can be in superposition with each other.
Hmm.
And by superposition means that it can be in a combination of a zero and a one and any arbitrary. So it can
Got
have a bit of zero and a lot of one,
it.
or vice versa. And when we actually measure them or when they interact with the environment, it actually ruins this property of quantumness. It ruins the quantum superposition. So when we are trying to think about designing systems that would be good quantum computers or good qubits, what we try and do is design systems that are very isolated from the environment so that they don't leak out this quantum information
Oh,
that'll
fascinating.
allow us to
Yeah.
do these sorts of quantum computing.
That's really cool. So at when you go down to the smallest scales and the kind of the realm of quantum mechanic effects, you have this property where things can, rather than just being in one state or another, they can kind of be both states at the same time, and that actually gives us the opportunity to, rather than just working in zeros or ones, kind of working in the superposition of zeros and ones, which opens up like a whole new category, I imagine, of problems you can solve and types of computation you can do. But that that property of like being either or fundamentally collapses when you observe it.
Right, exactly.
Interesting. And so that and just interacting with the environment counts as observation. Like why is it that the environment has the ability to collapse that?
Right. So basically, we want to leave this qubit, this system, as unperturbed as possible when it's doing the quantum computation. But any bits of information we get out of that system starts ruining the quantum coherence
Hmm,
of that system.
very cool.
So when I say that the environment interacts with it, well, one way of thinking is the environment is interacting with the system, or some of the information is actually leaking out of the
Wow.
system. Because if we know that the environment is interacting with it, then we know something about the information and the properties of the system that we're trying to study. So us either observing it or the environment observing it is actually causing this information to leak out.
That's so cool. So, I one thing I would love to hear more about is I know a lot of your work with quantum information sciences is relevant to another field and another search, which is trying to find and understand dark matter. Can you tell me a little more about how that works and why those two fields are related?
Sure. So we're pretty sure dark matter is there. There's a lot of indirect observational measurements that shows or hints at the existence of dark matter. So one of
Hmm.
the first observations was actually made by a physicist, Vera Rubin, and she was looking at the rotational curves of galaxies. So
Hmm.
how quickly our galaxies actually rotating. And you can make very accurate predictions of the rotational curves of galaxies if you know how much matter is inside the galaxy. So basically, what she did was compare these galaxy rotational curves with how much matter she could see.
Hmm.
So, stars and the planets are matter that we can see. And there was a big mismatch between what was predicted to be rotating in these rotational curves of galaxies and the matter that was actually
Wow.
observed.
Okay.
So that was where the first big hint of there being unknown matter that doesn't interact with light the way normal matter does. And that's where it gets the name dark matter. It doesn't interact with
Wow.
light.
So it's
Um,
just something
so
out there that we can't see, but we know it's there just because of how gravity in the universe is reacting to it.
Right.
Wow.
So
Okay.
it's mostly through gravity that we get the indirect evidence that dark matter is there. So it definitely interacts via gravity. Whether or not there are other interactions with our kind of standard model world remains to be looked
And
at.
what do we know about it? Like, do we know how big it is? Like, what do we know anything about it?
Yeah, so based on these big astronomical observations, we actually know what the total mass of dark matter should be in our universe. So we kind of know what the aggregate is. We know what the full mass of dark matter in the universe is, which is, by the way, far more than normal matter in our
Hmm.
universe. Um, but we don't know how big the individual pieces of dark matter are. So they could range from the size of a black hole all the way down to, subatomic scale. They could be the size of a proton.
Wow.
So that's one of the big unknowns in dark matter is, well, how big are the individual pieces? The second thing
Okay.
then that we do know about dark matter is, again, from looking at things like rotational curves, is what the velocity distribution is. So we do know how quickly dark matter is passing through the Earth.
Oh, interesting.
And so that actually also allows us to try and design experiments that would allow us to try and detect
Wow.
it.
So wait, so not only do we not like we can't actually see it, but it interacts so weakly with normal matter that it regularly just passes clean through like the entire planet.
Right. So we know it interacts via gravity, and we have some limits of how strongly it would interact via other types of forces. But these are incredibly weak. So
Hmm.
this is why we need to think about large experiments in order to have a very large
That's
target so that
remarkable.
it would interact with.
That's really amazing. I think, was aware that we didn't know all that much, but the fact that like there could be such a range of, I guess, just like very basic properties as simple as size and how much it weighs, and what the particles look like, that it makes sense that it's just such a difficult challenge to find something that fundamentally doesn't interact with the world that we are made of. What can you tell me about like why quantum information science is an interesting or like a promising realm for doing that?
Sure. So as I kind of mentioned, it can range in size from something that's as big as a black hole to something the size of a proton or even smaller. And so a lot of the existing state of the art experiments have looked for the bigger dark
Hmm.
matter. So it's easier to find bigger things.
Yeah.
So we're starting to think about looking for lighter dark matter. So smaller particles of dark matter, lighter masses of dark matter particles. But as we do that, as we start going to smaller masses of dark matter, actually, we need to have more sensitive
Hmm.
experiments. We need to
Okay.
have experiments that will be sensitive to very low masses or very low energy excitations. And actually, the relevant energy scales are those that happen in quantum materials.
Cool.
So the types of energy scales for these low mass dark matter particles are exactly those that happen in quantum
Whoa,
materials.
interesting. So in the absence, given that it seems like the big wimps aren't out there, we're shifting towards smaller things, and that the way in which they would be expected to interact with normal matter would produce the same kind of energy jumps that you're actually looking for in a quantum system.
Exactly,
Wow.
exactly. So it's the confluence of where the next generation dark matter experiments are going and where the excitations are in these types of quantum
Wow.
materials.
That's really cool. So what are some of the questions, I guess, like obviously the attempt to like figure out what size it is or what mass, dark matter has is kind of the first step. But what are some of the questions that you feel like are the most interesting, or like, what do you want to know about dark matter?
Oh, yeah. So of course everyone wants to detect it, and once we do detect it, that will be, I mean, that will be a huge celebration, I think, in general. But for me, I am a solid state physicist. I'm interested in materials and phenomena inside materials.
Hmm.
So for me, the mass is kind of a boring
Yeah.
thing to think about. We kind of know what the mass of lots of
Yeah.
things are. For me, what would be really cool would be, is there any internal structure in dark matter?
Oh,
So
interesting.
in the
Okay.
way that our periodic table of normal matter described by the standard model can categorize materials into lots of different classes, into lots of different properties. Well, is there like a dark periodic
Whoa.
table? Is
Yeah.
there a way of structuring or dividing dark matter into different types of dark matter? Does dark matter have different types of quantum numbers? Does
Whoa.
it have
Yeah.
spin?
Yeah.
So actually understanding like what the internal structure of dark matter is, and for me, like how do we design materials, or how do we design experiments in the realm of the matter that we're used to, that would actually start thinking about how to probe those properties in dark matter. That would be
Wow.
super fun for me.
That's fascinating. That's like, yeah, like the hunt for, the mass of dark matter, just interacting in it all seems interesting, and but it makes sense that mass is really just the tip of the iceberg. Like, knowing the mass of stuff in our world and in the matter in the normal matter world is like the least interesting thing about it sometimes. So that I like have never thought about the fact that there could be, this really entire almost parallel universe within our universe of like new elements, new ways of being, new. That's amazing.
Yeah, and the thing is, we really need to understand how our normal matter behaves, and what sort of properties of dark matter we could probe with our normal matter in order to answer that question. So, for example, if dark matter has spin, then we need to start thinking about, well, how does our normal matter interact with that dark matter, and how do we like think about designing and optimizing our normal matter in order to be able to start probing those sorts of
Wow.
properties.
So if we are to figure out some material that can act as kind of the bridge between our world and this
Yeah,
other world, we need to really understand our part of the equation so that, however it interacts will yield information.
exactly, exactly.
That's so cool.
That's how we know how our normal matter interacts, right? Our
Hmm.
standard model, which is how our normal matter interacts, is our way of describing our matter world around us right now. So this has to be the most obvious bridge between, the dark sector is what we call dark matter, between the dark sector and what our light
That's such
sector
a
is.
badass name.
Um,
That's awesome. Wow. Do we have, this is just, betraying my own ignorance, but like where is dark matter? Like do we know where to look, or like where to point the directors, or detectors rather? Like do we have any expectation of how fast it's moving, where it's coming from, just any of that information to go off of?
Right. So I did explain before that we kind of know what the total mass density
Hmm.
is, and we know that it isn't in clumps. So we do have some information that it isn't in like chunks or nuggets, and we do know what the total velocity distribution is. But what's interesting is we also, if we think about us sitting on Earth in our lab on
Yeah.
Earth, because we're moving, our solar system is moving, and our planet is also
Moving,
rotating
rotate.
on its own
Cool.
axis. We're actually moving through this dark matter,
Wow. That's so
as a
interesting. So dark
background.
matter
So
isn't hitting us, we're hitting it as we speed through space, and that kind of creates an effect of like a unidirectional wind of, wow, that is wild. Okay, sorry, go on.
yeah, so this dark matter wind is really useful for us when we're designing detection experiments, because it gives us a way of distinguishing between background signals and what would be a dark matter signal.
Hmm.
So if we can design a material with a directional or an anisotropic response, then we're actually able to pick out this directionality, which would be really a smoking gun
Wow,
of a dark matter detection event.
that's so cool. Wow, that's awesome. I look forward to the day when it finally works and we finally find it. I'm sure everyone else does. Can you, so I mean, barring, discovering the parallel universe of the dark sector, what are you excited for in this field? Like, what gives you awe, or what makes you get out of bed in the morning in your work?
So, aside from maybe discovering the dark periodic table, I think trying to find and understand new forms of matter is just so open ended,
Mm,
and um, that I think it was at the turn of the century, one of the founders of quantum mechanics said, with quantum mechanics now, chemistry is solved.
mm,
And I think the last few decades in solid state physics have shown that that's really not
mm.
true. That there's far more emergent properties in materials and in quantum systems that just can't be explained yet, or remain to be discovered and remain to be found. So I think this whole area of new matter, whether it's dark matter or just new forms of matter that we're aware of, is a completely open question. And so, yeah, so if that's not too broad a response, I would say
Oh
finding
no,
and discovering new phenomena and new matter.
that's so cool. Amazing. Well, thank you so much for taking the time to talk to me today. I really enjoyed hearing about your work, and I'm really excited to see what comes next.
Great. Thanks, Jeremy. It was great talking to you.